All right, guys, STAT1800. I guess the overarching question here is, what do we do when sigma is not given? Or not known? Well, first of all, we do not use a z interval. We do use, well, easy for you to say, a t interval. And oh, that's just ugly. I probably should start the video over, but I'm not going to. We use a t interval instead of a z interval. Now, what's the difference? Guys, a z interval has as its basis a z distribution. And a normal distribution is defined by its mean and its standard deviation. So if I know I have a normal distribution that has a mean of 100 and a standard deviation of 15, I know where it's centered and my variation, my deviation is defined. A t-interval. T-interval works differently. T-interval is defined by the t-distribution. So instead of using a normal distribution that we use when the population standard deviation is known, we use something called a t-distribution when the population standard deviation is not known. Guys, a t-distribution is defined by its degrees of freedom. And the lucky thing is the degrees of freedom is one of the easiest things to calculate. The degrees of freedom, which we abbreviate as just df, is found by just taking our sample size minus 1. So a normal distribution is defined by the mean and the standard deviation. A t-distribution is defined by its degrees of freedom. Now, and degrees of freedom is calculated using the sample size. So we talked about earlier, we said for a 95% confidence interval, when sigma is known, results in a z critical of plus or minus 1.96. Calculate the t critical, as you would expect would be t star for a 95% confidence interval when n is equal to 32. Now, n equals 32 tells me that my degrees of freedom is 31. So I'm dealing with a t-distribution. Now, one thing that the t-distribution and the z-distribution have in common is they are both centered at 1. But the z-distribution, the variation, is defined by its standard deviation, where the t-distribution, the variation, is defined by its degrees of freedom. So this particular t-distribution would be centered at 0, just like the z-distribution, but the degrees of freedom define the variation. So we want to find between which two values, negative t star in positive t star, capture the middle 95%. Now, it turns out this is, again, very easy to find on StatCrunch if you know where to go. And all you have to do is go to Stat and go to Calculator. Instead of scrolling down and stopping at normal, you want to go on down and stop at T. Now, I'll tell you a little bit about the history of T. There was a guy, his name was William Gossett. He was from Ireland, so I assumed that he probably drank a Guinness or two in his life. But what he found out when he worked with small samples where the population standard deviation wasn't known, that the simulations didn't match up with what the calculations for the normal distribution were actually given. So he developed this t-distribution, but legend has it that he worked, actually I think he did work for, maybe he did work for Guinness, but anyway, or maybe in my head I'm just wanting a Guinness, I don't know. But he was, for some reason or other, he had to publish anonymously. So he published this about this new distribution, which was more accurate than the normal distribution when the population standard deviation wasn't known and we had very small samples. He published under student T. So the T distribution comes from his anonymous pen name of student T that he was using to publish. For some reason he didn't want to be identified. And actually I think legend has it, and I don't know if this is true or not, but I think it had something to do with his employer didn't like the fact that he was taking time off his job to work on statistics instead of whatever his job was. And I really do think he actually did work at a brewery, but I may just be making that up too. All right, let's go to T distribution. Now you'll notice a glaring difference. So first of all, we need between. But you'll note a glaring difference. It doesn't give the mean and the standard deviation. It just gives degrees of freedom, df. So in our case, our sample size was 32. 32 minus 1 gives us a degrees of freedom of 31. And I want from, well, I want the area between to be 0.95. And I want to compute those values. So my left bound is negative 2.04. And then my right bound is positive 2.04. Okay? So it's as easy as that. I think it's worth maybe looking at, let's just come up with something, although you would never really see a wacky confidence interval like this. Let's say we wanted to do an 82% confidence interval where a sample size was equal to 10. So we want to find in the T distribution for degrees of freedom 9, between what two values do 82% of the distribution fall? Gang, it's just, again, it's easy when we've got this option in StatCrunch. Degrees of freedom 9, we need 0.82 and hit compute. So negative 1.45 and positive 1.45. Now the technical accuracy of your calculation, you would just go further out if you were making the calculations by hand. So guys, pretty simple stuff. Now let's come up with an example, and let's work through it and show you just how easy these T distributions are to use and calculate. So we would like to estimate the mean wait time at Tim Hortons from, let's say 6 a.m. I don't even know what time they open up, but from 6 a.m. to 8 a.m. So what do we do? Well, we'd start stalking Tim Hortons, right? We'd go over and sit in a parking lot, and we would choose some cars. And let's just say that we decide that we've got time to choose 30 cars. And we would kind of tag them. So as soon as, well, not literally tag them, but in our mind and in the organization of the, and summary of the data, we would tag them. So car pulls in. As soon as they get in that line, we say, okay, that black BMW over there got here at 6:04 a.m. and we would watch them until they got their order and pulled off, and let's say they got it their order 90 seconds later, so we would record that as a 90 seconds. Next car took a little bit longer. Let's say it took 122 seconds. Well, anyway, we would get all measurements for the 30 cars, and then we would do our summary statistics. And let's just say that the mean was 1.2 minutes with a standard deviation 0.3 minutes. Now, we only got 30 cars, but we're wanting to make a statement about all cars at Tim Hortons. Shoot, guys, I've lost my paper. I'm having a hard time keeping up with my paper for some reason. So we wonder right now, do we use a T interval or a Z interval? Well, it's really pretty simple. Z interval is sigma known. No. Well, guys, when sigma is known, we are forced to use the T distribution, the T interval, that student T, William Gossett, found many years ago. So, guys, it turns out that the T interval formula is X bar plus or minus. Now, we typically put a Z star there, and we would if the population standard deviation was known, but it's not, so we have to use a T critical value there. Typically, we would use sigma, but we don't know it, so we replace the obvious. Instead of using the population standard deviation, we use the sample standard deviation, still over the square root of n. Guys, this part over here, as I explained in a previous video, is still your point estimate. Everything to the right is still your margin of error. This is just your T critical, and you use the sample standard deviation because the population standard deviation isn't known. Well, guys, in our problem here about Tim Hortons, the mean was 1.2. The T critical, we'll have to go back and get that. So we want a 95% confidence interval. I don't think I specified that, but I'll go back and get that in just a second. The standard deviation is 0.3. And we stalked 30 cars that morning. So all I need to be able to calculate this by hand is the T critical, and in this case the degrees of freedom is going to be equal to 29, and let's say that we're estimate with 95% confidence. All right. So let's go to StatCrunch, get our T critical. So I want between, my degrees of freedom were 29. I want 0.95 between. So I have 2.0452, let's call it 0.0452. So I wrote that there. So guys, now it's just a matter of plugging in your calculator. You might say, well, we wouldn't plug in our calculator. I know. This is just an illustration to show you that how these things happen by hand, and then pretty soon we'll we will take care of this in Stat Crunch. So we have 1.2. I'm going to do the minus first. All right. And then I'm going to do the plus next. Just talking about Tim Hortons is making me hungry. Alright, so with 0.95 probability, it looks like the mean wait time at Tim Hortons. And guys, don't go out and publish this. I just made this stuff up. So yeah, Dr. Darbro did a study on Tim Hortons. No, I didn't. I just made this up as I'm going along. They probably give better service than this. So there's a 0.95 probability based on all this fictitious stuff I just presented to you that the mean wait time from 6 a.m. to 8 a.m. at Tim Hortons is between 1.08 to 1.09 minutes and 1.31 minutes. Now, how would we do this in Stat Crunch? How would we really do this? I wouldn't do this with the formula. I would use the calculator. Use Stat Crunch. So, guys, I'm going to go to Stat. Instead of stopping at Z-Stat, I'm going to go to T-Stat. One sample. And guys, in this case, I have summary. So the sample mean was 1.2. The sample standard deviation we said was 0.3. My sample size was 30. And I want the confidence interval 0.95. And compute. So you see we get 1.088 and 1.312 just as we did by hand. Guys, I think I would tattoo it to the brain that anytime I want a T interval, I'm going to plug that information into Stat Crunch and go for it. Okay. Now, I think I've got a, no, I don't have it either. I can go get some data. Well, I tell you what, let's do that in a different video. I think I'm gonna call it an end. I really think with the foundation that we have now in Z intervals that T intervals is not much of a stretch. It's just a different distribution, and it requires going to a different line. Go Z-Stat if you have the population standard deviation. Go T-Stats if you don't have the population standard deviation. Have a good one, guys.